Okay, thank you. Okay, so in the previous talk, Shai discussed the L function theory and the Grothendieck trace formula for the L function, and explained how to deduce from the trace formula and the general facts about the general machinery of the six-functor formalism for constructible sheaves, and how to deduce from all this, all the Weil conjectures, except for the Riemann hypothesis part. And the rest of this workshop will be devoted to proving the Riemann hypothesis part, which is the hard part, and the one which has some new ideas, techniques, and theory. So the goal of this specific talk will be quite modest. It will be to give a reformulation of the Riemann hypothesis, or maybe a statement which implies the Riemann hypothesis, but such which will be about push forwards of constructible sheaves, so that we can prove it using similar divisage arguments to the ones Shai sketched for the proof of the Lefschetz, for the Grothendieck Lefschetz trace formula. And this theory will be the theory of weights. And before we kind of jump in, I just want to recall the setup of that Segev talked about in his talk, but with some analogy between the algebraic geometry picture and the algebraic topology picture. So if I have spec of a field, then and I have the Galois group, the absolute Galois group of this field, then this thing, it's a Cal or pro-Cal site should be thought is pro-finite sets with a continuous action of G. And so sheaves on this thing valued in anywhere, any place, would be just objects with a suitably continuous action of G. And ignoring this continuity part, this is very much like just the groupoid BG, or the classifying space of the group G, which is the analog in algebraic topology. And if I take spec of K bar over this thing, so this thing has a G action, and in fact it makes this thing a G torso over this thing. So we should think of it as having a free action, and moreover, the pro-Étale topos of spec K bar is in a sense trivial. So there is some kind of a pro-finiteness issue here, but if we would work in the Étale topology, this would be in fact behave just like a point. So in algebraic topology, we think of this as the analog of EG, which has a space with a G action, and such that the map to BG is equivalent, and EG is contractible. So it's a contractible space with an action of G. This is the universal G torso in the world of algebraic topology. Now, if I have a scheme X mapping to spec K, so well, this just corresponds to a space X with a map to BG. So being defined over a non-algebraically closed field K corresponds in algebraic topology to have a structure map to the classifying space of the Galois group. And taking the base change, which is just the pullback of this diagram, of course, corresponds here also to the pullback of this diagram. And because this space is contractible, it's the homotopy fiber to BG. And the general theory tells us in both cases that we have an action of G on this fiber. And in topology, this would precisely identify X with the orbits, which are also the homotopy orbits of the action of G. So this is how we should think about our situation. So we are given something like this, which we really want to think of as something like this. In particular, if we have a sheaf on, if you have a sheaf on X, So F is a sheaf on X, and we have a map phi here, then we can define F bar to be pi star of F. It's a sheaf on, so F is like lives here, F bar lives here, and since it's pulled from X, it is equivariant with respect to the action of G. So what does it mean?
You mean to write pi for the map from X bar to X?
Yes, of course. Thank you very much. I decided in the last minute to kind of transpose my diagrams to fit whatever. Yeah, but thank you. So what does it mean?
Lior, can I ask a small question?
Sure.
So, are you implying here that spec of a field has trivial higher homotopy groups or something like that? Or
yes,
like,
it is true. Yes, the Étale homotopy.
This is true?
The Étale homotopy type of spec K bar is contactable.
Okay.
Yes, it's not only a pi1 thing, it's in fact the entire Étale homotopy type. So what does it mean? So again, ignoring the continuity issues, it means that when I pull for every element in the group, pulling F bar, since this is just pi star of F and G composed with pi is just pi, this has a canonical isomorphism with F bar itself. So it gives me an equivariant sheaf. Okay, so specializing to the case that K is FQ, then our Galois group is just Z hat. And this is the profinite completion of just Z. And it has a topological generator, like as a topological group, it has a generator by Frobenius, but we would like to take the inverse of the Frobenius, the thing which corresponds to the geometric Frobenius, just like in Segerstad. So it's generated by phi, or sorry, I should say FRG, the inverse of the map which takes X to X to the Q. And so if you go back to our topological situation, we may pretend that this thing is just BZ, and then what we have here is just a space with an action of Z, or just a space with a single automorphism, which is the geometric Frobenius, and up to important differences related to the continuity of the action and so on. This is just equivariant sheaf would be just a sheaf with a specified isomorphism phi like this. And in fact, in all our considerations so far, so when we computed traces of powers of Frobenius and combined them into a null function and so on and so forth, this is the only data that we actually used. And it is helpful to make it into a definition. So Weil sheaf on X is a sheaf F on X bar plus this thing. So the Weil sheaf F. So we think of it as something which is on X, though in practice it's a sheaf over X bar with a partial descent datum. So the reason why we want to work with Weil sheaves will be clear only in later talks. And basically, they will, things which appear in nature, things which actually come given to you from geometry, will be honest sheaves, not just Weil sheaves, because they will be pulled back from X. But to analyze them, we will have to construct by hand some auxiliary objects. And it's much easier to construct such an object without worrying about the actual descent datum. You can just like give any phi you want. So it will be important to work in this level.
Why is it a partial descent datum? Why isn't it all the things that you need? Like, what is missing for it to be a proper descent datum?
So, so one categorically, one is what is missing is a condition that this is appropriately continuous. And but yeah, let's say we don't want to worry about the condition. Let's leave it at this.
It is a
Difference
condition,
between
though. I think
Z
it's
hat
important to note that it is a condition. Like if you have a Weil sheaf, then it's a condition on the sheaf for it to be.
You're right. You're right. It's true and important. So it's good that we had the question and the correct answer. Thank you. So yeah, we don't want to worry about the condition of it being actually a sheaf.
And in the end, just one last comment. In the end, we will now work with Weil sheaf throughout, and it's important that it's a condition. So in the end, we'll have a statement that some version, which is for Weil sheaves, but it's important that I can always restrict to sheaves. Okay, yeah.
So please don't hijack my talk, okay? If you have a correction, say it. If you have like, general stuff you want to say, you can save them for after the talk. So every honest sheaf is actually gives you a Weil sheaf if you just remember this thing without any conditions. But there are some new examples. So for example, if I consider spec FQ itself, and I want a one-dimensional sheaf, then this corresponds just to a continuous homomorphism into QL bar star. So I'm considering QL bar sheaves. We'll need this algebraic closureness at some point. But a Weil sheaf. So this is a sheaf. But a Weil sheaf allows us just to have any map like this, which is the same as just saying where one goes. And basically, you can just choose any element. It can be like a transcendental element of QL bar star, and this will give you a Weil sheaf. We denote it by LB. And of course, not all of those LBs can be extended to something continuous on Z hat, and so not all of them correspond to actual honest sheaf. But
so what is the condition? Is it easy?
I don't know if it's very easy, but clearly if you take something, I think if you take something transcendental, it wouldn't work. I think even if you take something like,
it's not about transcendentality. It's about valuation. It's very easy for a L-adic number to be transcendental, right? There's really a lot of, right? It's a continuum.
Oh, sorry, you're right. Yes, it's more like it will not work for L, for example. It will work for Q, as we will see in a moment.
Yeah, the valuation of your element needs to be zero. That's essentially.
Yes, thank you. So, like Shaul started to say before I shut him up, was that it's important to know that in some sense, you can control all honest sheaves using Weil sheaves using honest sheaves, and only those simple guys which don't have to be honest sheaves. And we have a theorem which goes as follows. So for F Weil sheaf, there exists a filtration. So starting with 0, such that the successive quotients are all of the form some GI, which is an honest sheaf, twisted by this character sheaf for some PI. So it means that up to extensions, these things and twisting by characters, we don't have much difference between Weil sheaves and honest sheaves. So all kinds of arguments which we know how to prove for honest sheaves and we want to extend to Weil sheaves. If the thing we're trying to prove is kind of additive with respect to extensions and easy to verify for twisting by characters, we'll have this ability to extend our results to general Weil sheaves. And I will give an example for the Grothendieck formula in a moment.
Oh, there's a question here.
Yes.
The question is, what is the point of Weil sheaves if you do all this pro et al thing in order to remember the topology on QL, but then you forget the topology on Z hat? So what was the entire point?
Okay, so I don't know if I have a very good answer to this, but the point is that even for a Weil sheaf, I mean, you can still have this element P in QL bar star, which is a topological thing. And I mean, it's not like we forgot it. So we will discuss.
May I suggest a different answer?
Yes, of course.
Yeah. Okay. The answer is that when you do it if you do it over a spec of a finite field, you're right. It's a completely. You did a very long circle and went back to where you started it. But when you're going to work on an algebraic variety, you're going to see that the étale topos still have a topology that you only detopologize a small part of the story. There's a very big part of the story that you did. For example, if you think about, let's say, a local system, a very local system on GM, then the Z hat that comes from your finite field became Z, but the Z hat that has to do with the GM stayed Z hat. Okay, so that's the reason.
That helps a lot. Thank you.
Oh, okay. Now I understand the question. So yeah, so just to extend about what Tomer said, you know that say local systems like constructible things which are like locally constant on the whole thing without certification correspond to representations of the étale fundamental group. And now in general you have a fiber sequence of the étale fundamental group of X and X bar going to the étale fundamental group of FPQ, which is the Galois group, right? We have just a short exact sequence like this, which comes from the kind of a similar thing in topology, or a long exact sequence of homotopy groups. And so this is Z hat, and of course you can take Z here, and you can restrict to the corresponding group here, which is sometimes also called the Weil group of X. You know how to denote it. And so Weil local systems will correspond to representations of this guy. So you can see it still remembers the whole thing which comes from the geometry, but from the arithmetic we just did this decompletion of the fundamental group. So maybe this is more in line with what the question was about. Okay, so now I want to talk a little bit about duality and Tate twists, because this will also be important and also related to this thing with the characters. So there is a very specific sheaf on spec FQ, which comes from the action of the Galois group on roots of unity. So if I take FQ bar itself, of course, it has an action of the Galois group. This is trivial, but it also, if I restrict to roots of unity of order L to the M, so this is a certain finite abelian group on which G acts. And as an abstract group, forgetting the action, this is just a cyclic group. But the action is not trivial, and we denote this thing with a 1 like here. So it's called the Tate twist. It's Z mod L to the M, but with a non-trivial action of the Galois group. And if you take the limit over all these guys, then this is what it's called, just ZL hat 1. And of course, if we want, we can now rationalize it. But we can also like tensor with QL bar if you want. This is this guy. So, and we also define this thing to be like with the -1 to be just the dual thing. And of course, we can also just put any number here to mean the tensor power, and we can also define it for negative r's using the tensor powers of -1. So this is for all r greater or equal 0. And finally, if f is a sheaf on X, then we can define fr, the r-Tate twist of f, to be f tensored with QL bar R, where here I'm allowing myself to think of this guy also as a sheaf on X by pulling back along the structure morphism from X to spec FQ. So X slips over FQ. Okay, so now an easy, I don't know how to say it, claim.
Lior,
Yeah.
So twisting here only affects the action of the fundamental of the group, right? It doesn't affect like I don't know, the sheaf itself, the underlying sheaf without. I don't know if such a thing can be said actually, but like
it affects. It's tensoring with something which is pulled back from spec FQ. So spec FQ, it's, sheaves on it are just vector spaces with an action of the Galois group. So this is the only thing you can twist. So of course, it's something, it works the same over all points of X because it's tensoring with something which is pulled back from here. So the only thing it changes, like you say, is the action of the fundamental group.
Thanks.
So the claim is that the Weil sheaves corresponding to this guy is precisely this character sheaf for Q to the -R. So there are some signs here which are confusing. I made a great effort to make the signs work. Maybe I made some mistake, but I advise you to just believe me on that the signs work. And if they don't, so just pretend like they do, and maybe we can think about it later. So you of course need only to consider the case R equals 1 because of all those definitions are obvious, clear what they do on the action of the Frobenius. And in this case, so we just note that the geometric Frobenius is inverse to the map, which is defined by raising to the qth power, and on the roots of unity, which is a multiplicative group, a group with whose operation is given by multiplication. It is a multiplication by Q. So the inverse thing will multiply by Q to the -1, and the rest follows. Was that okay? Is there a question up until now?
Can you just like remind us what the LLA is for a number L?
What this thing is?
Yes.
Yeah, it's just what it's the Weil sheaf which corresponds to
sending one to the
yeah.
the thing.
So just saying that the Frobenius acts by multiplying with this element.
Yes, cool. Thanks.
Okay, now there is this general 6-functor formalism which gives you a bunch of functors, and there's also a symmetric monoidal structure which is compatible with those functors in a nice way. And using this formalism, one can phrase a certain Poincaré duality result, which is actually already used in Shai-Stokes, but I want to make a little bit more explicit. So first of all, I just want to remind you that for
is there a Verdier duality situation here also?
Yes, there is a Verdier duality situation.
Leo, can I just make a very small comment?
Sure.
reverse one comment? So what I was about to say earlier that just as we had 6 operations for constructible sheaves, we also have 6 operations for Weil sheaves, and constructible sheaves are a full subcategory of the category of Weil sheaves and are stable under all the operations. That's important.
Yes.
Thing I wanted to. Yeah.
Okay. Yes. Thank you. So I just want to remind you how this abstract thing is related to this thing with homology and cohomology. It was already said several times, but I just want to make it very explicit. If you have a sheaf here, and so the cohomology of X with coefficients in F is the cohomologies of the complex of vector spaces on the push forward of F. So that's how you compute cohomology. Just push to the point, and then you get a complex of vector spaces, and you can just compute. So this is X bar. And similarly, if you use here cohomology with compact support, then you get the same thing with the F lower shriek instead. And now there is a theorem, which is the Poincare duality in this world of algebraic geometry, and it says that if X bar is smooth and proper of dimension n, then the compactly supported cohomology degree k of F is its dual is isomorphic to the cohomology at degree 2n minus k of X bar with the dual sheaf twisted by n. I hope I got this correctly.
This doesn't require proper.
Sorry, I didn't mean proper. Thank you. And of course, if X is proper, then cohomology with compact support and cohomology is the same thing. So this is the non-proper version. And let me say something about the proof. It will be a cheat, but I just want to kind of really connect the things that were done in the previous talks to make sense. When we use Verdier duality, which tells us that in general, if you have also a sheaf on the target, spec F Q bar, then there is an equivalence between, so the sheaf hom F lower shriek and G, and what I want to write here, so let me write something stupid, hom F F G hom F upper star G. So this looks like you know, just the adjunction between the lower shriek and upper shriek. This is true if I would have written just ordinary hom, like the abelian group or something like this, or the complex. But I mean the sheaf, and to make sense of this, those two sheaves don't live on the same thing. What I need to do here, I need to push it forward to be a sheaf on the target as well. And this is a very abstract statement, which is true. And the key kind of is the fact that since X is smooth of dimension n, or maybe I say before, I want to specialize to the case that G is just the constant sheaf. And in this case, the exceptional pullback, QL bar, which we also denote like omega x, is QL bar shifted, twisted by n and shifted cohomologically by -2n. I believe this is the correct thing to write.
Are you sure about the minus?
Pretty sure. I think that what confuses you is that you think of the dualizing sheaf as the thing that you tensor with, but here is the thing in mapping to. So kind of, this is changes the 2n. I think this is what happens.
Are we proving a statement now about X or X bar?
X bar.
X. So this is a statement about X though, right? Because Tate twists are on X. I think you want to say that it's X, and this is an equivalence of like representations of the Galois.
Yeah, I wanted to say it in a slightly more convoluted way, but you're right. Maybe I just yeah. Of course,
Yeah.
well, it does make sense because you can pull it from X to X bar, but maybe I just say the whole thing.
No, but what does the twist mean?
No,
If you
this
like,
is the sheaf. This is the sheaf on spec FQ. Okay. I'm sorry for making it confusing. Let me just go one step back. This thing is a geometric thing. This works over X bar. You might wonder what happens without the bar. So what happens without the bar is that when you push to this thing, you get something with an action of the Frobenius. And you could also pull to X, and if you forget the action of the Frobenius, this is what you have gotten if you pull to X bar and push to spec FQ bar. But maybe it's better to say it like this, like Shaul said. Okay, so we get a thing like this. And if we take cohomology, then on this side, right? So if we just get, or maybe just let me complete the statement. So what we get is that F lower F linear dual is the same as F lower star of F check tensored with QL bar n shifted by -2n. And if you take cohomology, you'll get precisely this statement. So maybe a bit fast, but I hope you understand what's going on. So this check reverses the sign of the K because, you know, it kind of shifts things above 0 and below 0. And this n shifts. So maybe let me just make it even more. When I map, I get a thing like this. Okay, and now I believe I get something correct. If I take the cohomology, then this 2n is this 2n, and this minus is this check, and this n is this n, and everything works, I hope.
The only remark is that the way you wrote it, the equation above needs to have X bar on both sides, right? You have an equivariant isomorphism between this and this. That's what you did, right? This is what F does.
You are right. Okay, great. So we have a Poincare duality, which involves the state space, and the point is that the way it is related to the usual Poincare duality is that you really need to think of this QL bar n as the orientation sheaf. And when you close the loop in ordinary geometry, then you might have switch the sign, but in algebraic geometry you might have multiplied by some root of unity, which is not necessarily +or -1. And this kind of orientation sheaf is the thing that keeps track of that kind of information. Okay, so in Scheistok, he defined the L function of a scheme X, and let me just remind you how it works. So he defined L X F T. So I will use a only slightly different notation. So I'm going over all points in close points in X, and I call them X and not X tilde because I will not have the other kind of point. And what I'm taking here is the determinant of 1 minus phi x t to the degree of x acting on by x minus 1, where the degree of x is the degree of the extension on the residue field. And the theorem, the trace formula, gave us that if we have a morphism like this, then Lx ft was equal to Ly f lower shriek ft. And this was explained for constructible sheaves, but I just want to briefly explain how to extend this extension to Weil sheaves using this theorem I quoted above. And so this is a proof of extension to Weil sheaves, and the idea is very simple. So without going too much into details, you know, we have a filtration of our sheaf F such that the quotients are constructible sheaves twisted by some character. And the basic observation is that if you have a short exact sequence of vector spaces, which with an operator which is compatible, then the characteristic polynomial is multiplicative for such extensions, even if the extension is not split. So in general, the determinant of 1 minus t acting on V is just the product of, so in classical linear algebra, you prove this by, I don't know, upper triangulating your matrix or something like this. So this reduces to the case of an actual constructible, like an honest sheaf tensor, a character. And now what you observe is that the L function of this thing, the effect on the L function of twisting by a character is just you know, substituting bt in your variable, because this is exactly what you did. You said that the Frobenius now, the way it acts has to be multiplied by b, and all our normalizations were precisely so that this thing will propagate correctly when you multiply them all over. So this is like a sketch of the proof of this extension.
And then you have that constructible sheaves are that general Weil sheaves are extensions of constructible sheaves by with an action. Hmm?
Sorry, say it again.
Like, is it true that, like, if I understand your proof correctly, what you mean is that like Weil sheaves are constructible, okay, yes. This is the.
Yeah, so we have this like the controlling theorem which allows us to control Weil sheaves in terms of honest sheaves and twists.
The visage thing.
Yeah. Okay, so now let's recall that the Riemann hypothesis part of the Weil conjecture was, well, it was about the case to have spec x goes to spec fq, and you use the trace formula for this, and you start with the constant sheaf here. So what do you get? You get, so on the one side of our formula, just the L function of the constant sheaf without the star, the constant sheaf on spec x was just the ordinary zeta function of x, which is this product of a closed points of 1 minus t to the degree of the point. And the claim was that this is just this alternating product of polynomials, each of which is the characteristic polynomial of the Frobenius acting on the corresponding degree cohomology with compact support. So And of course, here n is the dimension of X. And the Riemann hypothesis part, was the claim that, well, first of all, you can identify the first and last polynomials explicitly, or just 1 minus t and 1 minus q to the n t, and more generally, for all k between 0 and 2n, all roots of EKT, all roots are of absolute value. So let me just say it like this: all roots lambda satisfy that their absolute value is q to the, well, I must write minus k over 2 because, you know, I mean, this number is the reciprocal of the root. So it might be confusing, but it's just like a short way to address those numbers as reciprocals of roots. And of course, you can see that it holds for 0 and 2n. And like Shai showed us, this thing also holds for the projective space, for example. Now, we would like, so for this theorem, it is essential that X is smooth and proper. So here we cannot avoid both the smooth and properness hypothesis. And the problem is that we want to prove it in a way which is similar to how we prove the trace formula by kind of a divisage, decomposing X, like fibering it over something which generically has a core over fibers, and then decomposing it to the open set on which we have the generic nice behavior, and a closed set which has a smaller dimension, and do some Noetherian induction. And those kind of arguments really don't work if you forget the properness, because this is like being compact is the one thing that is surely distracted when you pass to an open subset. And so for the remaining time that I have, which will be a bit over time, but not much, hopefully, I just want to explain.
You can take a few more minutes. We have a long break after Ariel's talk, so it's okay.
Yeah, I think I'll need like 5-10 minutes.
No problem.
We want to a reformulation of this theorem in a way which we can state for all Weil sheaves and without the properness assumptions, so that we can use this inductive divisage argument. And this is uses the following. Well, maybe. Yeah. Okay. So, what is this statement in terms of sheaves? So those roots are precisely, so observation, or maybe it's just a definition. These roots are, well, up to some normalization, just the eigenvalues of the Frobenius. So what we're actually trying to say is that the trace formula, when we push a sheaf, then we can also say something about what happens to the eigenvalues of the Frobenius. So you let's do the following definition. So definition. So for our definition, we would like to talk about the absolute value of eigenvalues of the Frobenius, but for a general sheaf, those are just numbers in QL bar. So since we don't know a priori that those are algebraic numbers, we need to do either of the two things, either to choose an isomorphism tau with C, or to go over all such isomorphisms. And this is precisely the thing we're gonna say. We're gonna say something about fixing such an isomorphism tau, but if you prove something for all such taus, then like we already discussed, this gives like the consequence of being algebraic and so on. So definition is as follows. So let's first assume that F is a sheaf on spec FQ to the D. Then we say that F is tau pure of weight omega if, so let's say it's an ordinary sheaf for a moment.
Lior, I just want to say I'll be talking a lot about weights and stuff, so unless this is relevant to something in your talk now, you can hold it off.
Say it again.
I'm saying that I intended to define weights and purity and such. So I mean, unless you need this for something of yours now,
I needed to phrase the Lin's theorem and to deduce the ordinary formulation of the Riemann hypothesis from it using Poincare duality. So it's pure of weight omega if all eigenvalues of the geometric Frobenius on eigenvalues lambda of the geometric Frobenius on F satisfy that when I apply tau to them, the absolute value is, well, it's the cardinality of my field to the power of omega over 2, which is just, of course, q to the power of d omega over 2. And I could say that q to the d is just q, of course, but I want to emphasize the fact that this is a thing which varies. It depends on the, it will depend on the.
Lior, just to clarify, you mean at all stocks, right?
So this is just spec fq to the d.
Oh.
Yeah, so this is just a vector space with an action of the geometric Frobenius. I just want to all eigenvalues of this to have some norm, and pure if tau pure for all tau. So specifically pure of weight omega if tau pure for all tau with weight omega. And I mean, the omega can depend on tau. So maybe of weight omega if with, whatever you need. So this is for an ordinary sheaf. So F, like a general sheaf on a general X, if for all X in closed point, I want that well, first of all, I want to restrict to the stock, and I want to consider the homology. The Kate homology is tau pure of weight omega plus k. Right, so I did two generalizations here. One that I want to work over a general X, and then I just want the condition at each point, which takes into account the degree of the residue field. And the second thing is that I want to allow a complex of sheaves, so it has cohomologies. And the thing I do is just I say that at each degree I require the pureness separately, but there is a shift which depends on the degree. Okay, so now with these definitions, we have something very simple to say. So QL bar, the constant sheaf on X, is pure of weight 0. Well, this is clear, just like the Frobenius X trivially. And Riemann hypothesis part, if you think about it, what it actually says, it says that when you push to a point, so F is the map.
So, Lior, just to clarify, Here by sheaves, you mean complexes of sheaves? You mean like the infinity category thing? Or
Yes, I do.
okay.
So I was trying to say ordinary when I mean the kind of a non-derived thing and a complex in general. But yeah.
Oh, okay. But so just to clarify, at the beginning of the definition, all sheaves are actual sheaves and not Weil sheaves, right?
In the beginning of which definition?
Of purity. So
no, I actually meant Weil sheaves.
Oh, you meant okay.
Yes, I'm kind of I saw it was a bit confused. The logic was, which was not very explicit, but let me say it now, was that once we defined Weil sheaves, we want to work with Weil sheaves all the time, and sometimes to prove things about them, we will need to reduce statements to honest sheaves and then somehow extend them back to Weil sheaves. But the point is that once we realize that what we actually need is only the action of the Frobenius, we are trying to work now only with Weil sheaves.
Yeah, no, this I understand. But my main point is that like pure sheaves are automatically actual sheaves on X, are they not? Like, are there any Weil pure sheaves that are not actually sheaves?
Yes, if you
Yes,
take
so
LB.
yes, so for example is LB. So
oh, because the weight can be arbitrary.
The weight can be arbitrary.
Yeah,
Exactly.
okay. Mm-hmm.
And this is in a sense would be the main issue, that the weight can be arbitrary. That you don't know a priori that the weight is such that you get an honest sheet. So if you think of it, the Riemann hypothesis, what it tells us that this push forward is also pure of weight 0. So it's just like a trick with language. We kind of packed everything in the definition of being pure of certain weight in a way that makes the statement exactly this simple, right? It means that on the Kate cohomology, it acts with q to the power of something over absolute value, q to the power of k over 2. Is that okay?
Yes.
Good. So the Riemann hypothesis will follow from the following purity theorem, which tells us that if we have, the same situation and X is smooth and proper, then, and we start with F is pure of weight and weight, omega, then a flourish F, which is also the F lower star, is also pure of weight omega. Yeah, so this is just really just a reformulation of the Riemann hypothesis for a general sheaf, but this does not address this thing that we need properness. And to address this thing we need properness, we need some kind of more technical notion. And the idea behind this technical notion is that while pushing forward sheaves along non-proper maps does not preserve purity and weights, it does, in a sense, preserve certain inequality on the weights. And once you're in a proper situation, coupled with Poincare duality, we could use a bound from below and above together, which will imply the statement that we want. So the actual definition that we need is that a perhaps tau mixed sheaf F.
Lior?
Yes.
So the little f here is again the map to a point in this. But and if you just have a proper map,
it will also work. Yes, of course. Yeah, this proper map, but I stated Poincare duality just for in absolute version. So just to use it to prove it, I will do it only in the absolute. So a tau mixed sheaf is of with weights omega 1.
Don't you need the map to be proper and smooth?
Yes.
Proper, right? Not only proper, like inclusion of a point, this will not happen, right?
Yes, instead of the absolute notion of smooth and proper, it suffices to have the relative notion of smooth and proper. So a tau mixed sheaf is such that with certain set of weights, collection of weights, is such that exists a filtration with the property that the successive quotients are tau pure with weight omega I. So it's a certain closing the collection of pure things under extensions. And even without the condition on having particular weights, being a mixed sheaf is a non-trivial condition. I mean, it's not clear giving a general sheaf how to filter it in a way such the quotients are pure. And the actual theorem
we do require the weights to be finite set, right?
Finitely many. Yes, everything is finite. All the filtrations will be finite, and all the stratifications will be finite.
Mm-hmm.
So the real theorem of Delin, which will be the thing that the rest of the talks will be devoted to proving, is that if x to y is smooth and f Weil sheaf on x is tau mixed, and I will denote it like this, that the weights of f are lower or equal omega. I mean, it's tau mixed for a certain collection of weights, all of which are lower or equal than omega. Then this push forward with compact support is also tau mixed, and with weights lower or equal omega.
You probably didn't mean to write smooth, right?
I didn't mean to write smooth. Yes, I guess I didn't mean to write smooth. Thank you. And so this is a statement which is possible to prove by kind of a divisage, so it will be complicated, but there will be sequence of reductions to a curve, and in the end to A1 over a point, and then there will be some computation that has to be done. Let me just, sorry for taking so long, but let me just finish with showing very briefly how the Lin's theorem implies the Riemann hypothesis, or even implies the theorem with the purity theorem. So if we start with the pure sheaf of weight omega, then it's particularly of weight, mixed of weight lower or equal omega. So this implies by the Lin's theorem that f lower shriek of f is also mixed with weights lower or equal omega. But on the other hand, we also know that this sheaf is the same as the push forward of the dual twisted by n and shifted by -2n dual. So this is Poincaré duality. So this is I could pass to cohomology. In the end, everything is defined in terms of the action on cohomology, but I can do it in the level of the sheaf itself. Now, this means that, so f check is pure of weight minus omega, in particular lower equal minus omega. And of course, there is no difference between the lower shriek and the lower star because we're in the proper situation. then this implies, so maybe before that, these operations, what they do on the weight, you can see that it just cancels, because the weight of the Tate twist was -2. So when I twist n times, it changes the weight by -2n, but the cohomological shift does the twist by 2n. So those things cancel out. So I get that this thing is also minus omega, in particular, lower equal minus omega. And so when I do f lower star of this thing, it's still has this property, but then it means that if I check it, it becomes greater equal omega. And so I have both these bounds, and now it's very easy to show that if you have a mixed sheaf of weight lower equal omega and greater equal omega, so you can kind of filter it by things such that successive quotients are pure of weight omega, and therefore the sheaf itself must be pure of weight omega. And this completes the proof. I think I'll stop here.
Thank you.